Alrighty guys, welcome back to MAC2311 Calculus Honors. Today is a fun day. It's Yiping's Student Teaching Day. And last Thursday or Friday, I had the pleasure of meeting with her and kind of walking through the slides and materials that she's prepared. She's put a lot of time into this, and I did get your emails, the ones from the weekend thing. I'm sorry I didn't respond to those sooner. I just saw them this morning. I had a busy weekend myself, but I've queued up all the YouTube videos that you sent me, and everything looks pretty good. Muffled again, huh? I think it's probably the audio issues you guys are hearing because the computer fan is spinning really hard. Yeah, it's the fan because the video file from my last class is still converting. Let me turn that on. And I'll also do the thing where we in a few seconds here, this should get better. There's the fan starting to quiet down. So Yiping split her lecture up into, I think, 17 different videos. Each one is pretty short. Each one's a very digestible little piece. After we play each little video, we'll pause for just a second. You guys can ask questions of her or of me, or Yiping. If you want to insert anything, just let me know. But I've got your videos, I think, all queued up here, ready to rock and roll. Is there anything you would like to say or do before we jump in?
No.
All good to go then? And can everybody tell me, has so the fan on the computer just quieted down because I killed the video conversion. Is this a little better audio-wise? You can hear better now? All right, very good, very good. Okay, then I'm going to just run through these videos, and after each one, we'll pause for a second or so to answer questions if you have any. But let's enjoy the lecture that Yiping prepared for us. Here's the screen share. Here's the very first video. Oh, let me back it up. Sorry, I was just making sure that it will play. We'll do it full screen.
Hello everyone, my name is Yiping. Today I talk about chapter 2.3 limit laws. First, I will talk about sum law, difference law, constant multiple law, product law, quotient law. Suppose limit x approach a of f of x and g of x exists, then 1. The limit of a sum is the sum of the limits. 2. The limit of a difference is the difference of the limits. 3. The limit of a constant times a function is the constant times the limit of the function. Limit of a constant is the constant. 4. The limit of a product is the product of the limits. 5. The limit of a quotient is the quotient of the limits, provided that the limit of the denominator is not 0. Sum law, difference law, product law, quotient law are separate. F of x and g of x. Put limit x approach a in front of each.
So that's the basic idea. Those are the fundamental limit laws. And they're useful because they let us take complicated limit expressions and just take the limit of each little piece individually. It says that the limit plays really nice with algebra, that you can just take limits of each piece of a big expression and then combine those to get the overall limit.
Power law and root law. 6. Limit x approach a, f, and of x to n. Limit x approach a, the whole number to n. 7. Limit x approach a, c is equal to c. C is constant at here. A limit x approach a, x is equal to a. 9 is 6 and a. Limit x approach a, x to n is equal to a to n, where n is a positive integer. 10 limit n root x is equal to n root a, where n is a positive integer. If n is even, we assume that a greater than 0. Square root 2 cannot take negative number in it, so n is even. We assume that a is greater than 0. Limit n root f of x is equal to n root limit x approach a f of x, where n is a positive integer. If n is even, we assume that limit x approach a f of x greater than 0.
So really what we're saying there is similar to in the previous video, that we can split limits up. And even with exponents, if you have some expression raised to a constant power and you want to take the limit of that whole expression, you can kind of just shove the limit inside, take the limit of the inner function and then raise it to that power, even if that power is like 1/3 or 1/4. The only thing you have to be careful of is running into domain problems. So here we have some worked example.
Limit x approach to sum of x plus g of x. We can use the sum laws. Limit x approach to f of x plus limit x approach to g of x is equal to 2 plus 0 is equal to 2.
Let's see. So let me pause really quickly. I think we haven't shown them the problem yet, so maybe this video is not in the order that we wanted. Let me see. We didn't miss one, right?
I can show the problem.
Yeah. Where did this problem come from? Do you remember the video number, or is it somewhere else? Let me make you a host so you can share if you like. So this particular problem, I think, is coming from the textbook, right?
This one.
Okay.
Homework number 48.
So what we're going to do here is we're going to look at each of these graphs and use them to figure out each of these limits, right?
Yes.
It would be nice if we could display the problem and the solution at the same time. Let me pull up your PowerPoint. You can attach to one of these. We already have it there. All right. And then would you like me to pull up the PowerPoint and have the video play beside it, or how would you like to do this? Do you want to do it over top of it live?
I can do it myself.
Okay, yeah, I'll let you take over then. I'm sorry. So if it's okay, I may annotate here just a little bit. In the first part, we're looking for the limit as x approaches 2 of f of x plus g of x. And the way she's going to do that is by splitting it up into the limit of f of x as x approaches 2 plus the limit as x approaches 2 of g of x. We'll find those two things separately and then add them. Sorry, so go ahead. You can let it play. It's all right. Yeah. This is a little bit of this. So we see she split the limit up into the limit of f plus the limit of g. And then each of those limits she's getting from the graph. So it's a little bit tough to see, I know, but if you look carefully, as x gets closer and closer to 2 on the f of x graph, the y value is getting closer and closer to 2. And that's true from the left and from the right. And the same is true for the graph of the function g. As x gets closer and closer to 2, the y value is approaching a clear value there, and that value is 0. You can see the coordinate axes by the little arrows. And then you can go ahead and let it play. She's going to do the same thing for each of these. So you just split it up, find the limit for each one from the graph. Yes, these are from the textbook. The same sort of thing happening here, but now we're taking the limit as x goes to 1. So we split it up and then just take each limit on their own. You're good. You can let it play. I'll just little tiny things like that. So you see where she's hovering her cursor now. There's a problem with the function g as x gets closer and closer to 1. From the left, the value on the graph is getting closer and closer to, it looks like, 2. And from the right, the value of g is getting closer and closer to, it looks like, 1. So the limit from the left and the limit from the right of the function g of x at x equals 1, they're not the same. So even though that first limit, the limit as x goes to 1 of f of x, that exists and is fine, it's equal to 1. The limit as x approaches 1 for g of x does not exist because the left behavior and the right behavior are different. Okay, so the limit overall here does not exist. You can let it keep playing. I'm just going to say, we saw that the limit of the second function does not exist, which means that the limit overall does not exist. So if you have something that comes out to a nice number plus something that does not exist, that object overall does not exist. And that's the abbreviation DNE that we saw the other day. Alrighty. So that last little bit there, you're good, you can let it play. We shove the limit under the square root. Then we distribute the limit to each of the two pieces. Then taking the limit of each piece. The limit of the constant 3 is just 3. And the limit as x goes to 1 of f of x, we see from the graph again, is 1. So each of these examples is just applying those rules where you kind of pull apart whatever the expression is you're trying to take the limit of and give the limit to each piece. And it may be a little bit subtle, but every single one of those steps, every time she wrote an equal sign, there's an application of a rule, It is fairly straightforward. You want to make sure that you get those rules into your notes, and that way you can refer back to them anytime you're a little bit stuck on a problem. So remember, with these limits, the limit as an operator is very nice. It's linear. You can split up over addition, subtraction, constant multiplication, but it's also plays nice with all the other algebra operations. You can shove limits inside of roots or pull them out of roots. You can shove limits inside of any constant power or pull them out of any constant power. And then the other thing to remember is that power functions themselves play very nice with limits. So the limit of x to the n, as x goes to a, is always just going to be a to the n, as long as a to the n is defined. All right, Bing, would you like me to go back to the YouTube video now, or what would you like to do?
We can go back to the YouTube video.
All right, so I'm going to turn off your share here, turn my share back on, and then we'll come back over to the next pre-recorded bit. So this is what we just went through. I think this would be next then.
Direct substitution property. If f is a polynomial or a rational function, and a is in the domain of f, then limit x approach a f of x is equal to f of a. Let's do the homework number 24.
So that's actually a consequence of what we just said, that if f is a polynomial or rational function, and we have those rules for splitting limits up and according to their pieces, then any polynomial or rational function, you can calculate the limit just by plugging in. And I think here she's going to work those two examples that we saw on the previous slide.
Limit x approach 3 4 multiple x cubed minus 5 multiple x squared minus plus x minus 2. We can use the sum law, product law, and also difference law. But here we already learned direct substitution property. So we just plug the number into the polynomial function. So multiple 3 cubed minus 5 multiple 3 squared plus 3 minus 2. 4 multiple 27 minus 5 multiple 9 plus 3 minus 2.
So there what we see is you have the choice to pull apart and use all of those rules independently, but because those rules imply this direct substitution law, You don't need to, right? You don't need to write down every step where you take the limit of each term of the polynomial separately and then pop the constant out of each term of the polynomial separately. You know how that's going to play out because those rules tell you that each of those things, you're going to pull them apart, pop the constants out, and then just replace x by the value of the limit. In this case, and in any case like this, where your function is kind of nice enough, like a polynomial or a rational function, you know you could always go through those steps and they would always do the same thing as just plugging in the number. So we just plug in the number instead.
We can get the answer is 64.
So instead of splitting this up and taking the limit of the 4x
Is
cubed,
the
5x
direct
squared, x into 2,
substitution property always can use? No. We can, let's talk about homework number 35. Limit x approach minus 24.
so we'll continue this one in the next video. The challenge we're going to run into in this next problem is if you try to just directly substitute, if you try to just plug in the limit, then the function becomes undefined because you have a 0 downstairs. So instead of just plugging in, we're going to have to do some algebra to try and reconfigure the function before we plug in.
And here, if we plug minus 24 into the equation, the denominator will equal to 0. This equation is undefined, so we cannot use the direct substitution property at this exercise. How can I do? So I will use the other way to cancel x plus 24. And here we remember there has an equation is a square minus b square is equal to a minus b multiple a plus b. Do you remember? So here we can use this because this is square root. We want to cancel the square root. So we can do this.
Another name for this trick is multiplying by the conjugate.
We multiply equation or number. Make the numerator and the denominator is the same. So actually this equation is equal to 1. So we use this equation. It becomes x squared plus 49 minus 25 squared. You don't need to do anything here.
Good, good,
Because we
yeah,
just want to cancel what we
very
have.
good. So this is a good teachable moment, right? It's not always necessary to distribute and multiply everything out. If you think ahead, remember what your goal is. Our goal here is to cancel the x plus 24 from the bottom. So rather than multiplying that bottom out, what we should really do is clean up the top and then see if we can factor out an x plus 24 to cancel with the bottom. And the way that that top looks after we combine the two terms, 576 happens to be 24 squared.
And here we can use this one. We can use the equation again. A squared minus b squared is equal to a minus b multiple a plus b. Square root 576 is equal to 24 squared. 24. So x minus 24 multiple x plus 24 x divided by x plus 24 multiple square root x squared plus 49 plus 25.
So we're a little short on space there, but you see what she's done is
Yeah.
factor the top.
Cancel up and bottom x plus 24
Yeah, we can cancel the factor here with the factor here.
is equal to limit x approach minus 24 x minus 24 over square root x squared plus 49 plus 25.
Very good.
We can plug minus 24 in the equation.
Very good.
We can cancel the common factor up and bottom 2. So it's equal to minus 24 over 25.
Very good. So if there's one thing I would take away from this particular example, these algebra steps, they can take a little bit of time. But if you're trying to take a limit of an expression that looks anything like this, right, you've got a radical and then maybe some other piece over here, and then some factor downstairs that goes to 0 when you plug in the x value of your limit, you should try multiplying by the conjugate, which is what's going on right here. So the conjugate of the square root of x squared plus 49 minus 25 is the square root of x squared plus 49 plus 25. You change that minus to a plus, and then because of this difference of squares rule, which usually you use to factor things, you're taking the a minus b and you're slapping on the a plus b. And that will always give you something very nice. In particular, the square roots will cancel. And that's where your square root goes away in this step, because you have the x squared plus 49 under the radical times another x squared plus 49 under the radical. So your square root goes. And then also the middle terms cancel out. When you think of it as foiling, right, F-O-I-L, the outers and the inners will cancel beautifully. You'd have minus 25 times that radical from your inners and plus 25 times that radical from your outers. So we don't even need to write them. They go away. And you just end up with the difference of those squares. And in most of these problems, they'll be constructed so that the resulting thing upstairs factors and cancels with the piece downstairs. If you're looking at random things, arbitrary problems, there's no guarantee that that's going to happen. But this multiply by the conjugate trick is a very useful trick for giving you equivalent expressions that don't have radicals like that. All right. Now I'm a little bit concerned about time here, so I'm going to bump the play speed up to like 1.5, or I'll slow it back down if we
If
need
f
to.
of x is equal to g of x,
That's too
when
fast.
x is not equal to a, then limit x approach a, f of x is equal to limit x approach a, g of x, provided the limits exist.
So if you have two functions that differ at
The
one
other
point,
way, we can explain it like that.
the limits will be the same.
F of x and g of x have the same behavior, except at x is equal to a if the limit exists. That implies that limit x approach a f of x is equal to limit x approach a g of x. We can see the graph back here.
And this is a kind of counterintuitive idea that the value of the limit doesn't, we've said before, the value of the limit doesn't depend on the value of the function at that point. It depends on the behavior nearby. But what this says is that you can change one value for a function. You can move any one point on a graph around, and it won't change the limit of that function there or anywhere else. So if you have two functions that are identical, except maybe at one particular point, they'll have the same limits. And when we multiplied by the conjugate and did all that algebra and canceled, that's what we were doing. We were coming up with another function who didn't have a hole. So the original function that we were playing with there was a hole in the graph at -24. And what we did with all that algebra and cancellation is come up with a new function that is almost identical to the original, only difference being it didn't have a hole in the graph.
But there has the other graph. We can say if there has a graph,
No, we don't.
f of x And also there has the other graph. It's the same with f of x. We call this g of x. It look like the same graph, right? We call that they have the same behavior, but only difference at a x is equal to a, f of x is a whole at here. When x is equal to a, g of x has that a at here, no whole. But we talk about they have the same behavior. So limit x approach a, f of x, still the same limit, x approach a, g of x.
And this is that core idea that we were talking about last week, that the value of the limit doesn't depend on the function value there. It depends on the behavior nearby. So if you have two functions that have the same behavior near a, even if they take different values, the limits will be the same.
Theorem 1. Limit x approach a, f of x is equal to L if and only if limit x approach left side a, f of x is equal to L and is equal to limit x approach a, right side a, f of x. We already know that limit x approach a, f of x is when the limit x approach a from the left side f of x and limit x approach a from the right side f of x have the same behavior. We talk about it is equal. So when limit x approach a f of x is equal to L, limit x approach a from the left side f of x is equal to L, is equal to limit x approach a from the right side f of x. Theorem 2. Before we talk about theorem 2, let's talk about the other concept. The greatest integer function gives the integer that is lower and closest to the number. But limit x approach 3x does not exist. What is the greatest integer function? Let's see.
So this guy over here is also sometimes called the floor function. He returns the integer, the whole number, that is less than x, but the nearest whole number that is less than x. So his graph ends up looking like this. And the example here is that the limit as x goes to 3 of this function, we're looking right here, does not exist. So here, she's going to show us the details.
Also, that is a piecewise function, right?
Yes.
Greatest.
Yes, definitely piecewise.
Integer.
Make sure we keep this sharp enough. Sorry.
Function, we always use the hot blanket to describe. When x is equal to 2, the greatest integer 2 is equal to 2. When x is equal to 2.3, the greatest integer 2.3 is equal to 2. When the x is equal to 2.5, the greatest integer is equal to 2. Because in the concept, the greatest integer function gives the integer that is lower and closest to the number. Lower and the closest to the number.
Okay.
And x is equal to 2.9. The greatest integer 2.9 is 2. When x is equal to 3, the greatest integer number is 3. Let's see the graph.
So that's kind of where we're getting the graph from. We can think about all these ordered pairs. Between 2 and 3, those are all the numbers that we were just looking at, right? Like 2.1, 2.5, 2.9.
Let's look at
The output is always 3 there.
yeah. Let's look at the graph, the greatest integer. Here we already talked about when x is equal to 2, the greatest integer is 2. It's here. When x is equal to 2.3, the greatest integer is at 2. When x is equal to 2.5, the greatest integer at 2. When x is equal to 2.9, the greatest integer at 2. So the graph is a 9 here. But when x is equal to 3, we find a hole at this point. But at the same time, you saw it has the legs graph. We can see from the x approach to 3, from the left side is equal to 2. The limit x approach 3 is equal to 2. And the x approach and the limit x approach 3, right side is equal to 3. We say they have different behavior. So since B and E not exist, limit x approach 3 does not exist. Theorem 2. If f of x is less than equal than g of x, when x is real A, except possibly at A, and the limits of f and g both exist as x approaches A, then limit x approach A, f of x is less than equal than limit x approach a, g of x. Let's look at the graph.
So this last theorem here that we're sneaking up on, the squeeze theorem, says that limits obey inequalities. If f is smaller than g, then the limit of f is smaller than the limit of g, as long as everything plays nice enough, right? As long as the functions are sufficiently well behaved for the limits to exist. And the theorem right below that, called the squeeze theorem, says if you have three functions, all, one smaller than the other, smaller than the next, then you can kind of sandwich or squeeze limits in between each other.
We have a graph g of x. We have the other graph. F of x. From the graph, we already know f of x is less than equal than g of x. When x is equal to a, they have the same behavior at L. So we can say the limited x approach a, f of x is less than equal to limit x approach a, g of x.
If the one graph sits entirely above the other graph, then the behavior of the one at A has to be at least as big as the behavior of the other at A. In other words, limits cannot break inequalities. And this is especially interesting when you look at something called the squeeze theorem.
The squeeze theorem, which is sometimes called the sandwich theorem or the pinching theorem, is illustrated by figure 7. It says that if g of x is squeezed between f of x and h of x near a, and if f and h have the same limit L at a, then g is forced to have the same limit L at a. Let's read example 11.
So there's a fun version of this in France. They call this the policeman's theorem. And I'll very quickly do this and then we'll get to her last example here. It says that if there's a policeman walking behind you and there's a policeman walking in front of you, and they are both going to the police station, then you are also going to the police station. The idea is that these two functions are like h and f are going to bound the middle function g near a. If those two outer functions are both going to the same y value as x approaches a, then the middle function must also go to that same y value. This is really useful when you're trying to take a limit of a function that's hard to work with, like the sine 1 over x thing that we saw.
We already know the graph of sine period is 2 pi. Always y-axis always -1, fill in -1 and 1.
There's one full period of sine. But we've seen that if you start
Because
scrunching the stuff up,
Sin x is greater and equal than -1 and less than equal to 1. This is the graph of sin x. So sin 1/x is greater and equal -1 and less than equal than 1.
another way of saying that is, you know the sine function is only capable of spitting out numbers between -1 and +1. No matter what's inside the sine function, it's only able to spit out numbers that are between positive and -1. You can think of it as coming from the unit circle, right? Sine values are always just y values on the unit circle, which are always between -1 and 1. So sine x, sine 1/x, sine 10x, sine pi/x, they would all be bounded between -1 and 1.
We want to solve x for sin 1/x,
And we're looking as x goes to 0.
so that we plug x squared to this equation.
That's the idea. You start with -1 is less than sine 1/x is less than 1, and you multiply through by x squared. So if you take this expression right
X
here,
squared multiple all the
multiply
sides.
everything by x squared, you get this.
We already know limit x approach 0. X whole is equal to 0. X approach 0 minus x squared is equal to 0. They have the same behavior. So we say they are equal. And reduce the sandwich, or we can call this Creed theory. When limit f of x when we can say this one is we can say this one is f of x. This one g of x. And this one is h of x. If f of x less than equal than g of x and less than equal than h of x and limit f of x limit x approach 0 or a f of x is equal to limit x approach a h of x and it is equal to L then limit approach A, G of X is equal to L. You already know G of X is square sine 1 over X. The behavior X approach 0 is equal to 0.
Very good. All right. I think that's everything, right? So first things first here. Let's thank Yiping for being very brave, going first with the student lecturing. That is always hugely intimidating. I think this is a challenge. Delivering a lecture is a challenge always, especially in this sort of setting, especially if it's not something that you've been doing a lot. So big thanks to Yiping for delivering this in a way that made it very intelligible, gave us sources that we can go back and review. I'll post links to all these videos under today's announcement, along with the link to today's total lecture. There's one last thing I'd like to share with you guys before we go, and since we do have just a few minutes here, I'm going to do that. There's a notation that I kind of like for those squeeze theorem limits. So let's take a quick look. As we saw there, it says if f of x is less than or equal to g of x is less than or equal to h of x for all x near.
I cannot see the camera.
I'm so
It's
sorry.
not
I'm
on
so
the
sorry. Here we
paper.
go. Yeah. So just restating the squeeze theorem here, it says if f is less than g is less than h for all x near a, then it's true that if the limit as x approaches a of f of x is equal to the limit as x approaches a of h of x, if they have that shared value, call it L, then the limit of the middle function must also equal L. So kind of like if the policeman behind you and the policeman in front of you are both going to the police station, then you are also going to the police station, right? The example that Yiping did there is nice. So we want to find the limit as x approaches 0 of x squared times the sine of 1 over x. Obviously, we cannot use direct substitution here. Because what on earth would be 0 squared times the sine of 1 over 0? 1 over 0, this is undefined. So sine of 1 over 0 is very undefined. How do I take the sine of something that doesn't exist? That would be a real challenge. And indeed, this function, x squared times sine of 1 over x, it is not continuous at 0. It's not even defined at 0. So we have no hope of plugging in and just using direct substitution. We can't do that. But we know that sine 1 over x, this is the big word, is bounded. Right? It's a bounded function. We've looked at the graph of that function on its own. We proved that at 0, it can't possibly have any limit. The sine 1 over x itself oscillates back and forth really wildly in here, and then eventually it starts to chill out. Oscillates back and forth really wildly in here, and then eventually it starts to chill out. So this is one of those situations where kind of pulling apart the limit and working with each individual piece makes it worse rather than making it better. right? All the examples from earlier in Yiping's lecture, we were able to calculate the big limit by pulling it apart into each little piece, and then each little piece was manageable, and then we put it back together into the big limit. Well, here, this little piece is not manageable. It's really, really badly behaved near zero. But somehow multiplying this nasty thing by x squared makes it nicer. Particularly, it's bounded between -1 and +1, right? Here's the graph of sine 1 over x, but it never goes outside this -1, +1 window. And this is true for both sine and cosine, regardless of what's inside of them. -1 is less than or equal to sine or cosine of anything, right? It could be anything in here. Doesn't matter. The sine function can only ever spit out stuff that's bigger than -1 and smaller than +1. So even though the thing inside here is really nasty, the sine of that thing, sure, it's nasty, but it's bounded. It doesn't get big. And then you can multiply everywhere by x squared. And generally with these squeeze theorem problems, this is what you're trying to do. You're trying to find some limit that is hard to figure out, but one piece of your function is bounded. So you'll start with an inequality for that piece of your function, which you know is always true. And then you'll do normal algebra to that inequality to make your function show up in the middle. So now here in the middle, after multiplying by x squared, my function shows up. That's the thing I'm trying to take the limit of. So this is a good inequality to apply the squeeze theorem to. Now here's my favorite way to do this. You can say, yeah, I'm going to take the limit of this function and the limit of this function separately. And if those come out to the same thing, then the middle guy has to have that shared value. I like to take limits everywhere in the inequality, because that's what our previous theorem said. It said if f is less than g, then the limit of f is less than the limit of g. In other words, you're allowed to take limits through inequalities. Right? So I start with an inequality that I know is true. I do algebra to make my function show up in the middle. Then take limits everywhere. The limit of the function on the left, we can calculate by a direct substitution. That's 0. So 0 is less than or equal to the thing in the middle is the thing in the middle. It's the thing I'm trying to find. And the limit on the right, we can also calculate using direct substitution. If I plug in 0 for x there, I get 0 squared, which is 0. So my limit has to be both larger than or equal to 0 and also smaller than or equal to 0. Therefore, this guy has to be 0. The only way to be both greater than or equal to 0 and less than or equal to 0 is if you are 0 yourself. And then the very, very last thing I want to do is show you this and some similar graphs in Desmos. So I did tease these the other day. Sine 1 over x we know is a monster. It's not a nice function. Really badly behaved near 0. But because it's bounded, if you multiply by something which itself goes to 0, that decays the amplitude enough. So even though it's bouncing back and forth, the frequency is getting very, very high. It's wiggling very, very quickly. The amplitude is getting squished. And the fact that we're squishing that amplitude is enough to get us so let's do this and then So the fact that we're squishing the amplitude down, it's the x squared factor that's squishing the amplitude down. And in fact, we can say what it's squished between. Here's my upper bounding function. And here's my lower bounding function. So let's come over here. X squared sine 1 over x, that's the red. And then x squared itself is the blue. Negative x squared is the green. So the red, no matter how weird it gets in here, and it does get weird, make no mistake about it, we zoom in on this shit, it doesn't stop looking weird, it just looks weirder and weirder. But because it's always beneath the blue, and it's always above the green, and the blue and green both go to the same y value as x goes to 0, the red must also be going to that y value, just in its very strange, bouncy way. This is the power of the squeeze theorem. If you have a well-behaved function, like x squared, multiplying a bounded function, like sine 1 over x or sine of anything, then the well-behaved function kind of controls the bounded function, even if the bounded function wants to jump around. The money step here is right here. This is where we use the theorem that says if f is less than or equal to g, then the limit as x goes to a of f is less than or equal to the limit x goes to a of g. So you can take limits through inequalities. Limits cannot break inequalities. The one thing a limit can do is it can turn a strict inequality, like if this was f is strictly less than g, the conclusion here would still be a less than or equal to. So limits can take strict inequalities and make them weak, but they cannot flip them over or break them. All righty. So you now have everything you need to wrap up that homework set from last week. Remember the homework that I released last Monday, I didn't actually make that due until this Wednesday because we wanted to make sure that you guys had a chance to see Yiping's lecture on limit laws before getting to that. Please get into that homework if you haven't already, finish it up. I'll be publishing a new homework set for you today, which will be due next Monday. And we'll just keep going like that. I think I'll let you guys, as a calc class, I'll let you kind of manage your time on your own. So we'll just do the one homework set per week, at least for now, unless we have something that's urgent that I really need you to work on quickly. Is there anything we'd like to ask before we wrap things up here today? Yeah.
Will you post such a video chapter 2.4?
Yes, I will. I know I haven't uploaded that yet, but it will be up a little later today.
Will you spend one more class talking about chapter 2.4?
We will look at some more things from 2.4 on Wednesday. So on Wednesday, I'm going to prove some of the limit laws here using those rigorous definitions. So we will talk about it a little bit more. Alrighty then, I'm going to go ahead and sign out for today. If there's anything else you guys want to talk about, you can always come see me in office hours. And yeah, David the dog is indeed fun. It's just a little bit crazy. But that's it. Thank you guys so much. Thank you, Yiping, for all the work you put into your lecture. Remember, if you haven't sent me your student teaching section or your honors project topic, you need to do that by the end of this week. So I got a few emails over the weekend with with some topic requests, and just keep me in the loop with what you're thinking about doing. We'll make sure everything gets sorted out. All right? Take care, guys.